Computer. So these are the words we're going to go through. We're going to define them and show examples of what they mean. And as we go through this, I'll show you how they relate to our concepts of math, the order of operations, and everything else we use in mathematics. So understanding where it came from hopefully makes it easier to understand how to use it today. Knock on wood. Let's see. Okay, as we see in the first set, on the first page. Oh, let me tell you what the objectives are for this first section. This first section is called, this is chapter 2, section 1, reasoning and logic, and introduction. Our objectives. We're going to describe, and hopefully you'll learn how to define, how to recognize, and how to use quantifiers. Bless you. And their effects on statements. And we'll define what statements mean in a second. We're going to look at and examine different forms of statements. We're going to learn how to determine if two statements are logically equivalent. Notice I didn't say equal, I said equivalent. There's a big difference. We're going to learn how to develop logical arguments. And we're going to learn how to determine if an argument is valid. And then we're going to learn how to do that. I mean, how do you think we do that? How would you define, how would you determine if an argument is valid or not? You can't say just because I said so. It's my argument, it's valid. But what are facts? Because if it was pure facts, we all have to have an agreement of what facts mean. If we all agree on what facts meant, then there wouldn't be an argument. Because remember, every statement made, the person making it believes it. I mean, if that was the case, then we wouldn't have a bipartisan government. If everybody believed the same thing, which they say they do, but they don't. So, how do we go about doing this? It goes back to what we started off with here. What is a statement? Let me look at your little sheet here. We'll go through these words first, and I'll show you what they mean. Because if you look at the second page, you'll see stuff you've never seen before. Whoa, gotta fix that one. Uh-oh. I gotta fix those two. Anywhere there's a box, I have to fix. But you notice how we use these symbols here? What do they mean? Have you ever seen them before? In context of logic and mathematics. So, for example, let's see, this one is P. That's what I think this one's supposed to state. Let me see. Where? Oh, well, I'll make it up. What do you think that means? How would you read that? P, pointy arrow down, Q, pointy arrow. Now, this is what, how would you read this? They're symbols, aren't they? Until we learned we knew what those symbols meant. We didn't know how to read that, what it meant. Same thing here. This is what logic's all about. Because in logic, it has to be universally true to be true. If there's one mistake in there, then it's not true. That's called a counter argument. So we're going to learn how to solve these also. We solve these by truth tables. So let's look at these words. Let's first define a statement is a sentence that is either true or false, but not both. And we're going to define what true and false means later on. Negation, that little symbol there, that little symbol is called a tilde. If it's in front of something, it changes the truth value of that statement. A quantifier. What is the first five letters? What does quant mean? When you see the word, the letters QUNT, what does that mean to you? Like quantitative, a quantifier. What do you think that means? It's sheets. The second one has 2 pages, or the one that says chapter 2, section 1 notes has 2 pages. Was the one that looks like this, that starts off with this, okay, yeah, will have a second page that looks like this. Or it may have it. I don't know if it came out or not. It didn't? Okay, it didn't print out. Okay, I'm sorry, you should put it back down. I'm sorry. So a quantifier, whenever you see QNT means a numerical value. You quantify something means you're making a value of it. Quantitative analysis means you're analyzing it numerically. As opposed to qualitatively is when you analyze something on its quality, it's on people's opinions and what they think. So that's what we're going to look at that. Universal quantifiers, existential quantifiers. We're going to define all these in a second. compound statement, conjunction, disjunction. You've heard these words before, I hope. Now we're going to learn what they mean. A negation changes a truth table. So, in other words, if something is true and I negate it, it becomes false. Do we have something like that in mathematics? What's that? What is it? Because remember, I'm always interested in the why. You're right, we do have it. In other words, if I give you a 5, what's the opposite of 5? That's the negation. That's what that thing does. It changes it from 5 to -5. Quantifier gives the information about how many in the statement in which they occur. So the quantitative is numerical value of it. Universal quantifier. These are all, every, or no. That deals with everything in what we're talking about in our universe there. Refer to each and every element in your set. Because we're going to look at sets now to define these things. Existential quantifiers. Some and there exists at least one. Refer to one or more, or possibly, but not necessarily all the elements. That's what we call the existential. In other words, it's at least, it could be all of them, doesn't have to be all of them, but it could be some of them. It's doesn't sound too accurate, does it? It could be, it doesn't have to be. Compound statement. What do you think that means? Two or more. What's a compound statement in English? When you have 2 points to make. Compound statement is a statement that combines 2 or more statements or 2 or more arguments. Conjunction. Use the word and. Uh-oh, there's that symbol. That's that little pointy arrow up. That's the and symbol. Disjunction is the or statement. That's the pointy arrow down. And we're going to learn what those means. And yes, they do have meanings in mathematics. The truth table. This is what we use to summarize the truth values of a statement. Then and only then can we determine if it's true or false. Used to summarize the truth values of a compound statement and to determine whether 2 statements are logically equivalent. Not equal, logically equivalent. Means that if and only if 2 statements have the same truth values in every possibility statement. Here's a symbol we use for the logically equivalent. It's the triple equal sign. And we're going to see what that means in a minute. A tautology. A tautology is when all truth statements are true. All statements of a set. The values of all statements are true. Even if you have a compound statement, so tautology is if the final outcome are all true. A paradox, you've heard that. A paradox is when true and false happens at the same time. The event happening and the negation of that event happening. Also, that's a paradox. Can you give me an example of a paradox? The paradox is when you have a statement that is both true and false. Tautology is when you have all the results are all true of if you have compound statements. Give me an example of a tautology. What is something that's always true? Can you say if it's bright outside, then the sun is out? What about nighttime? Have you ever been inside in a parking lot when it's super bright, or a stadium and it's super bright? Was the sun out? No. So that's not a true statement. Give me an example of a tautology. Hmm? That's not a statement. Well, that's not a compound statement. That's just a time. What about that time? You sure? Then a time. If I unplug that clock, will it stop? That's what we call time. When I ask you what time it is, what do you do? Look at the clock. But I know what you're trying. I know what you're trying to say. But I'm saying this. These are kind of things that we have to try to look at. So give me a paradox. How do you mean? Yeah, but give me an example. You're just restating the definition. But that's not paradox. Those are different events occurring. I know it's think of a paradox. I know you've heard them before. Give me a statement that's both true and false. For example, nothing exists. Think of what that means. Nothing exists. In order to exist, you have to have something there, right? But what by definition is nothing? Nothing exists. That's a paradox. I know. Too early in the morning for logic. A tautology is when you have two statements and the outcome is always true. For example, a tautology, two statements could be it's either day or night. Those are two different statements. Day, the the conjunction is or night. It's either day or night. It's always true. Can it ever be not true? Can we have a day without day or night? So that's a tautology. I know these are the kind of things that this is what's so cool about logic is you have to think about it. The stuff we thought we knew, do we really know it? De Morgan's laws of logic. You've seen this also. Okay, this tilde symbol, when you read it as not. So De Morgan's basically, if I had this, if this is P, and how would you read that? Not P. I just told you it's not P. Whenever you see that little tilde, you read it as not. So this means not P. A paradox could be P and not P. They both occur at the same time. But no, we've seen this before. It's called the distributive property in mathematics. If I gave you this, what would the distributive property tell you to do? So what would it become? Or you can say negative x plus negative y. Both are true statements. Right. That's exactly what De Morgan's law is all about. It said not P. What's that symbol mean? If it points up, it's what? And so if not P and Q, then that's the same thing as saying not P or not Q. Because if you think about this, this is P and Q, or X and Y. Not X and Y means not X or not Y. That's the distributive property. That's how it works in mathematics. I know, it's too early in the morning. Conditionals or implications. In this one, we use this symbol. Conditional means if then. You grew up with this in every part of your life. If you clean your room, you can go outside. If you do your homework, then you'll get a passing grade. If you ace the exam, then you'll pass. That's a conditional. It also works with not. If you don't clean your room, then what? You can't go outside. You don't do your homework, then you can't pass. So again, that's a conditional. Equivalence of a statement and its counterpositive. What do you think a counterpositive is? What do you think the word just sounds like? Counter positive. Yeah, it'd be the fallacy of an argument or a statement. Right. The implication P the implication P then Q and its counter positive are logically equivalent if P then Q is equivalent to not P then not Q. Not Q, not P. Notice, this is important. Notice how it's stated. This is if P then Q, but the negation of that is if not Q, then not P. Why is that different than that? Why is this one not this one? If P, then Q. If not P, then not Q. Because this one tells you if P, then Q. The only way you get Q is if you get P, right? So if you don't have Q, that means you automatically don't have what? P. That's why this one is a truism, a true statement. But this one's not necessarily true. Are there other ways to get Q? Yeah. This is just one statement on how you can get Q. So, for example, if it's sunny, then you can go outside. If you don't go outside, then it's not sunny. If you don't go outside, then it's not sunny. Well, that's not true. If you don't go outside, then it's not sunny. So does your not going outside dictate what's going to happen outside? No. That's why this one can't be used because there are other extenuating circumstances for it. A biconditional statement. It's two arrows. This is read if and only if. That's actually what we use in mathematics is the equal sign. Again, in chemistry, if you ever taken chemistry, you learn something called stoichiometry, which means the balancing of equations. This is true, and this is true. That's what that means. So it goes both ways. So you've heard of Venn diagrams, haven't you? What are Venn diagrams? And how do you represent them? A Venn diagram. Like this. Yeah. I know you're going to point at it. These are called Euler. That's how you read this. Euler diagrams. It's a Venn diagram without a universal box. What's a universal box? In Venn diagrams, you have to have a box around it because you have to define what your universe is. Then you can have your two statements or multiple statements. You can even have three or four or five or whatever. Because whatever's not inside of all these has to remain in the universe. An Euler diagram only deals with the statements. There is no other anything outside it. That's in other words, when you do an Euler diagram, you don't have to put a box around it. And that's what differentiates the two. If you use a Venn diagram, you have to state what the rest of the universe is. Whatever's not included inside these circles or they're overlapping, you have to put there. Right? Then the valid statement. Valid. A reasoning or an argument is valid if the conclusion follows unavoidably from the hypothesis. If the conclusion follows from the hypothesis. What's a hypothesis? Very good. That's a good way of saying it. That's exactly what it is. Have you ever made hypotheses in your life? Give me an example of one. Hypothesis is a statement made from observations. Yeah, I see that. Yeah, it'll work. The first one you get to when you're growing up is the leaves are changing color. That means what's going to happen? Season's going to change. It's beginning of wintertime. I mean, the nature knows what's going to happen long before we do. If you ever had any survival training or ever went camping, look what the animals do. If you see the ants and other animals getting closer to trees, that means there's going to be a big old storm coming. They want to get closer to a tree where it doesn't get as wet. If the ants want to stay out in the middle of the field, guess what's going to happen to them? They're going to get flooded. and they're gone. So yeah, they know these things because you can tell by atmospheric changes. The older you get as well, you ever hear of grandparents say, "Oh, my elbow's hurting. It's gonna rain tomorrow." And trust me, that's a true statement. Your body feels these atmospheric changes. Well, it's when we have you hear if you ever watch the news, you hear of high and low pressure systems. You ever think what that means? A high and low pressure system? Here's our Earth. There's two of them. And the clouds are up here. The clouds, the clouds are not up there for any reason. It's just being up there. They're at a specific altitude because what are clouds made up of? Water, yeah, and other impurities, but water. Water has a weight. So the atmosphere supports this weight at a certain altitude. So when you have a high pressure system, it's bringing it down. A low pressure system lifts it up. If it gets too high, guess what you have? Remember last week when we had fog in the morning? When you're in a fog, you're inside the clouds. Actually, the clouds are on top of you. So you're seeing what pretty much pilots see in a very small scale. But when you come up here, why would it start raining up there? If it gets up there, why would it start raining? It has to do it because what's happening here now, when you take a cup, a glass, and you pour an ice cold drink in it, what happens to the outside of that cup? What's that called? Condensation. That's exactly what happens here. You have a warm cup, and eventually, the higher you get, temperature drops. It can be 70 degrees down here, but at 14,000 feet, 15,000 feet, guess what temperature it is? Below freezing. The higher you get, the colder it gets. So that's what's happening. So this water, the higher it gets into a colder atmosphere, it condenses. So all these water molecules start getting binding and it just drops. It gets too heavy for the clouds. And what's really cool, I'll ask you for next time, I'll look for a YouTube video where you see a cloud, all of a sudden it just lets go. It reaches what's called saturation point when it just drops. And all this water at one time just hits the ground. And that's what happens when we have rainstorms. I'm sorry to get away from that. But I thought it was interesting. So here we have examples of Euler diagrams. How do we know the Euler diagrams? No boxes. Very good. So this one, for all A that are in B, all A are B, what does that mean? Yes. Yes. So A is a proper subset. We'll talk about subsets later on as well in the next section. But since all of A is inside B, that means, are they equal? Why not? Very good. B can have an answer that's not in A, but all of A has to be in B. So A could be real numbers. B could be the set of all real numbers and alphabet letters. So that's what so in other words, this little ring out here, that's the alphabet. That's what it means. And we're going to define sets in a minute. No A or B. So they have nothing in common. Disjoint sets. Some A or B. This is what we're used to seeing. Where they overlap is what they have in common. Some A are not B. Some A are not B. Yeah, that's this area here. These are the A's that are B. These are the A's that are not B. Likewise, what would you say about this side? Very good. B's that are not A. Exactly. So let's look at these statements. If P, then Q. If P, then Q. The converse of that statement. No, converse is not sneakers. It means the opposite. If Q, then P. The inverse is just the opposite of the two. How would you read this? If not P, then not Q. Very good. That's the inverse. A lot of people get converse and inverse mixed up. Converse is you just flip them around. Inverse means you negate both of them where they are. Contrapositive. If not Q, then not P. And then the biconditional P if and only if Q. Q if and only if P. So they have to go both directions. So it's important. You have to know what each of those mean and how they represent. Because when you make statements, that's what we're looking for. Okay. Here's a statement and its negation. These are universals. All x's are y's. All x's are y's. The negation of that, some y's are not, some x's are not y's. Is that what you'd think it would be? The statement is all x's are y's. How would you negate that? When you negate it, you're making it false. Some x's are not y's. You see the difference of the two? This one says all x's are y's. If at least one x is not a y, that's a negation of it. You've just disproven it. No x is y. Some x's are y's. If this one says absolutely no x's are y's. All it takes is one. Instead of some, we say if at least one. That's instead of some, you can put if at least one, but less than all. Some x's are y. This one says no x's are y. Some x's are not y's. All x's are not y's. I know what you're thinking. You were thinking that these would go together, but in order to negate something, you have to prove it just one piece is opposite. So this was saying some. What does some mean? It could be one. You can't use the some x's are not, because if you only had one, that's it. You can't. So it has to say no x's are. None of them, period. So that takes care of the one possibility. So yeah, it's I know how you feel like, because I did the same thing when I first learned this 40 years ago. It's the opposite of all or no is some or none. The opposite of some is no or all. So the opposite of this is some. The opposite of some is none or all. The extremes. Let's look at these. Let's look at truth tables. Let me first define what truth tables are. So, for example, if I had P, the statement, this is a statement. It can be either true or false. Here's another statement. Q. It can be either true or false. What statement is that one? P and Q. With now, let's look at the true statement for this. Well, also let's look at the negation. So if P is true and false, what would not P be? What would the first one be? So if P is true, not P is false. If P is false, not P is true. It's the opposite of it. Opposite is the negative part of it. So now let's look at this. The and statement. You have two statements, the and. The easiest way to think of this we have two possibilities here. And here we have little handles. The and statement is this one. If I pour water here, okay, if it's open, it's true. If it's closed, it's false. If I how many possibilities are there of P and Q? How many combinations can you make? Remember, they could be either true or false. They could both be true. We can have true, false, false, true, or false, false. Those are all the possible outcomes that you can have with binary conditions. So let's look at the and statement. What this one says, both of these, this is P and this is Q. If they're both open, will water come out? Yep, so it's true. If this one's open and this one's closed, will water come out? No. If this one's closed and this one of water is open, no. If they're both closed, will water come out? So there's a truth table for the and statement. Why is it this one straight down? Because they're both in the same pipe. They both either are open or they're closed, or a combination. So this is the and. The or is this one. If I want to look at P or Q, in other words, what I have here They can both be true, true, false, false, true, or false, false. This is P and this is Q. So this first statement says what? Are they both what? Open. If they're both open and I put water in both of these tubes, will water come out? Yes. If P is open and P is cubed, I pour water in both of these tubes, will water come out? Yeah, because this one's open, it'll come out. In the or statement, I mean, is the third one. If the first one's closed, second one's open, and I pour water in there, will water come out? The only time water will not come out is if they're both closed. Why is this one the or statement? Well, because I'm given the option. I can either pour water in this one, or I can put it in this one, or I can put it in both. It's the statement you use. I can use this one or this one. That's what I'm doing here. I can choose which one. This one, I could put water in this one, and I have to put water in the first, this the same one. So I have two pitchers. They both have to go in the same one. So that's why this one's an and, this one's an or. So far, so good. Let's look at some combinations of these things with the negation symbols. Do the truth table of this one. Now, the tricky part about this is because you have to think through this stuff like you do mathematically. You have to think step by step by step by step. The first thing we have is a P and a Q. We have two variables. They could both be true, true, false, false, true, or false, false. Because we're dealing with two different variables. If we dealt with three, we'd have four more sets. So in order to build this, what's the first thing we need? Reading left to right, what do you do first? You have to find the not P. So what's not P going to be? Well, look at the P column. This would be false, false, true, true. That's the not P, right? We have the Q that's already there. So now we can put them together. So we look at now these two columns. False or true? Is it what goes here? False or true? Think of the pipes. If one of them's open, what happens? It goes true. It goes all the way through. Okay, the second one, not P is false. False or false is false. True or true, true or false. You have to build your equation up. So we have a P and a Q. So they're both true, true, false, false, true. So why do I always start off with this set here? Why? What do I what do I first thing look at is I have P and Q. What do I do this first? Exactly. Because I have to know what I'm dealing with. What are the possible values for P and Q together in a pair? What else do I need to build? Order of operations. Not Q. Very good. So the not Q is going to be, so there's Q. That's true. So it's false, true, false, true. I just changed I just changed all the values of the Q column. So I have the P, I have the not Q. I can now put them together. So I look at this and this column. It's an and statement. The and statement was that single pipe. True and false. So, or in other words, open and closed. Closed. No water. Open and open. Closed, closed. Closed, open. False. Because in the and statement, the only time it could be true is if they're both true. If one of them is false, then it cannot be and true. So far, so good with this. Let's do one more. Let's do that one. Let me see if we have enough time to do all these. We should be able to. It's true, 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 false, false, true, false, false. The first thing we have to build is what? Order of operations. What do you do first? Inside the parenthesis. Yeah. So we have to do inside here. So we have to do the not Q. You see where all this stuff leads to the current level of math? Because this stuff taught us order of operations. So not Q would be false, true, false, true. Then what do we build? We have P, we have not Q. What do we build next? Not yet. Have we finished everything on the inside? No, we haven't done this whole thing. So we have to do P or not Q. We have to do the parenthesis part. We have to do what's inside the parentheses. Order of operations. So we look at these two columns, P and not Q. So this is a statement and or. Or. So true or false, true. True or true, false or false, false or true. So we built this statement. The next thing we got to do is build what? Yeah, the negation of the whole thing. We just have to negate this last column. So it becomes what? False, false, true, false. It's just the opposite of those. That's how it works. It's exactly the same way mathematics does. Let's use this equation here. Because somebody said this earlier when I was doing these, and I said, okay, what do you do first? You said distribute. Let's see if they're logically equivalent. So if we distributed this, we would distribute it to everybody in there. So it would become what? Not P, not or, not Q. Very good. What's this called? You're absolutely correct. What's that? Yeah, but it's got another name. We use it in English also. I will not go out of class. Double negative. That's exactly what that is. You're absolutely correct. It's a double negative. And you're right, it's cancellation. But that's what's happening. So this would really be not P. What's not or? And Q. So what we're going to do now is we're going to look at these to see if they're equal. We've done this one already. This one was P, Q, not Q, P or not Q, the negation of P or not Q. All I care about is this last column here, F, F, T, F. Because this is, we will to compare if they're true, if they're equal, we only look at the last column. So that's this side. Let's build this one now. So we have P and Q. Going to be true, 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 false, false, true, false, false. Let's build it. What do we need now? We need the not P, right? So here's P. The not P would be false, false. Very good. So far, so good. Then what do we got to do? Yeah, now we can find the whole thing. Not P and Q. Now, this is pretty important. So P and false and true. Remember the and? This is and. That's that single pipe. So this is open, closed. Will water come out? No. So it's false. True and false. Will water come out? No. True and false. Shut up, Arthur. Yeah, I was trying to get these two. We're looking at these two. You're absolutely correct. I was taking you on the wrong journey there. True and false, or actually, it's false and true. False. False and false. True and true. True and false. So do these look like these? Yes. That's then they are equivalent statements. Pretty cool.
How do you determine true and false when it's an and statement? Like, how do you determine if it's true and false?
How do you mean? In this, I said that's why I start off with this. I start with my conditions, my A and B are P and Q. You go through all possibilities. They can both be true, true, false, false, true, false, false. And then from there for the and statement. Once we once we get the true and false possibilities, so we look at if they're both open, then water comes out. If one of them is closed, water can't come out. So that's how you look at it. You have to look at each one conditionally as separately. Because you can also have we can also have bigger equations like this. How would we start this one? Yeah, we don't throughout the whole thing, we only have P and Q. Since we only have two, the number of rows we're going to have, since we only have two, N is the number of letters. So since we have only two, two squared is four. We're only going to have four rows. This is the formula for the number of rows. If I had three letters, P, Q, and R, how many rows would I need? No. No. 2 times 2 times 2. Now, yeah, so that's what this exponential means multiply the base that many times. So we need 8 rows that time if we had 3 letters. So now we begin our journey. We have the first thing we build is P or Q. True, 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 false, false, true, false, false. This is the or statement. So true or true, true or false, false or true, false or false, false. The or statement is if we have that 2 tunnels, if either one. I know, yeah, I heard you say, no. So we built this one. Now we got to build this one. So first thing we need there is not P. So we look at the P column and just change letters. False, false, true, true. We built that. We have Q, so now we have to build both of those together. So not P or Q. So false or true, false or false, true or true, true or false, true. The or, if in other words, if either of them, if either is true, the answer is true. In the and statement, the only way to be true is if both are true. Okay, so that's so now we have this inside built. Now we got to negate all that stuff. So we go to this one and negate it, which means it becomes false, true, false, false. Now we do the entire thing. P or Q and not P or Q. Now we're doing both of these with an and statement in the middle. So we look at this row or this column and that column. True and false. Are you asking or telling me? It's false because remember, for the and, the only way it can be true is if they're both true. If one's false, it's false. True and true, true. True and true, true. False and false, false. That's how you build these things. You have to construct it, which is exactly what we do in mathematics. We have to work inside the parentheses, work our way out. We haven't talked about the conditional statements yet. We got it. This one?
Yes, that one. Wouldn't the second one be false?
So we look at this column. This is false. So the opposite of that is true.
But didn't we flip the or into and?
Inside there?
Yeah.
Well, if we would have done that, then we would have gotten P and not Q if we would have distributed. But we just did this one. We had the inside built. All we have to do there is just negate it. That saves us a little bit of time. We could distribute it and we get the same answer, but since we built the inside first, then we just negate it. Real quick, let's do the conditional statements. If then, in other words, P then Q. The only way to get an F is by going down, which means from true to false. In business, the only way you can get an F value is if you're going from a T to an F. In other words, if you're going from T to F, the answer is F. Everything else is good. Think in business. This is my example of a condition. This is the true and this is false. True is good, false is bad. And if you're in business, we have true, 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 false, false, true, false, false. If you're going from P to Q, and if you're staying on the same level, is that good or bad? No. If are you losing money? Only way in business is bad is if you're losing money. Are you losing money if you're going the same level? No. So that's good. So this is good. How about if you go from P to Q, if you go down? You're losing money. Is that good or bad? So that's a bad. If you're going from false to true, that's good because you're making money. But if you're going from false to false, is that good or bad? Well, no, actually, it's good because the only thing worse than being poor is being broke. So as long as you keep the same amount of money, you're doing good. Like if you go to Vegas, if I'm losing, if I'm still losing, but I still have money, I'm doing good. The only way it's bad is if you lose all your money. So again, the only way it's bad is if you're going down. That's a conditional statement. Unfortunately, we have to call it a day there because I think my next class wants to storm in and learn math. I don't know why. But we'll pick up from here next time.